Now that we've introduced the rules for integrals involving exponentials, I wanted to try out some of those rules with the following problems. So we're going to start with the integral of e raised to the 4x power, dx. Now, in a situation like this, we do have a composition of functions here. So what I'm going to do is let u be equal to that inside function, and I am referring to the exponent of this exponential. So u would be equal to 4x, and du would be equal to 4 times dx. Now, solving for the differential dx lets us know that we can substitute dx as 1/4 of du, meaning that we can set this integral equal to e raised to the u power times 1/4 of du. Now, 1/4 is a constant multiple and therefore can be pulled outside of the integral, so this would be 1/4 of the integral of e to the u du. The antiderivative of e to the u with respect to u would simply be e to the u plus a constant. Substituting back gives us 1/4 of e to the 4x plus a constant. Now, in general, because we did have a linear exponential up here, we can make this a more general rule, but this only works... hang on. I can't talk and spell at the same time, apparently. More generally, if you were integrating e raised to the, we'll just call it mx plus b power, then making a u substitution of u equals mx plus b is going to yield the following. It'll be 1 divided by whatever the slope was times e raised to the mx plus b power, plus whatever your constant of integration is. Now, in this case, because the slope was 4 due to the 4x, that's why we see a 1/4 as part of the final answer. All right, next example. This time we're going to be dealing with some exponentials that are not base e. We have the integral of 2 to the x times the quantity 1 plus 5 raised to the x dx. Now, we don't have anything for taking the integral of products at this point, but we will be getting to that early on in Calc 2. So first thing I'm going to do is distribute that 2 raised to the x power and then use a property of exponentials. Property of exponentials says that if you have two bases that are both raised to the same power, then you can combine those into one single thing. So 2 to the x times 5 to the x, I can simply multiply the 2 times 5 and have it raised to the x power. So we'll call that 2 to the x plus 10 to the x dx. Now at this point, we can use the rule for exponentials that are not base e. If we were differentiating these, we'd be multiplying by the natural log of the base. Because we are taking the antiderivative, we will be dividing by the natural log of their bases. So this will be 1 over the natural log of 2 times 2 to the x plus 1 over the natural log of 10 times 10 to the x power. Tag on a plus c, and you got yourself a good-looking final answer. Now, I do want to try one more example involving some exponentials. This one is going to involve one more use of the substitution rule. This one is the integral of e to the x times the cube root of 2 plus e to the x power. Now, I do see that we have a composition in the form of the cube root of something that's not simply x. So I'm going to let u be equal to whatever's on the inside. So that'll be 2 plus e raised to the x power. Differentiating this, du, would give us e to the x times dx. Thankfully, we have an e to the x right here, and we have a dx right here, and putting those together, that'll give us a du. Additionally, with that du, we will also have the cube root of, well, this thing that's inside, we referred to that as u just a moment ago. Now, because this is a radical, we are going to be thinking of it in terms of a power. So we'll change the cube root of u into u to the 1/3 power so that we can apply the power rule. Power rule says increase the power of u by 1. 1/3 plus 1 would be 4/3, and then divide by that new power. Or in this case, we'll say multiply by the reciprocal. Because we're done with the integral and it was indefinite, that's why we're going to tag on our plus c at this point. So overall, this is going to give us 3/4 times u, which was 2 plus e to the x power raised to the 4/3 plus c. And that will be our final answer. Of course, anytime you're interested in checking any of these indefinite integrals, it's simply a matter of taking the derivative, so please feel free to check should you care to do so.